Welcome to part 2 of Module 201B. Since we've looked at what an inductor is and we've looked at what inductance is, we're now going to look at the process of induction. Michael Faraday stated that anytime that we have a magnetic field and a conductor interacting with each other, we'll have an induced voltage within that conductor. So whether I take a magnetic field and cross it across a conductor, or if I take a conductor and pass it through a magnetic field, either way, that interaction of a moving magnetic field going across a conductor creates an induced voltage. If you take the example of a generator, we have a conductor that moves through a stationary magnetic field. However, with a coil of wire, as my current changes, the magnetic field within that coil also changes. And this means we have a moving magnetic field going across a stationary wire. Either way, both of these things will produce a voltage. Anytime that a conductor carries a current, it also creates a magnetic field that is produced at a right angle to the direction of the current. So as my DC wire, for example, carries a current through it, it will show a magnetic rotation around that wire. In my AC system, however, since my magnetic field is directly dependent on the strength of the current, and my current is constantly changing, my magnetic field inside my AC system is also constantly changing in respect to what the current is doing. So as my current rises, my magnetic field is growing out. As my current falls, my magnetic field is collapsing back in. So I have a constant change of not only magnitude, but direction of my magnetic field. It's important to understand that induction can only occur when there's a change in either the magnetic field strength or the position of the conductor. If I have no change, I have no induction. Therefore, either my magnetic field has to move or my conductor has to move. If I consider my DC circuit, as I close the switch on my DC circuit, I have a current rise from 0 amps up to whatever the maximum amperage is according to my resistance. As that is growing from 0 to the maximum, I also have an expanding magnetic field happening around that wire. Now once I've reached my maximum and my magnetic field is no longer changing because my current is stable, I don't have any induction. Induction has gone away and my circuit is dealing directly with resistance and resistance alone. As I open the switch, my current is collapsing from maximum down to 0 almost immediately. And in that case, I have a rapid amount of change happening in my magnetic field as well. And as my magnetic field collapses in the opposite direction, I also have a large induction with an opposite polarity. This is useful to us in a few different ways, but there's two typical types of induction that we deal with. The first one is mutual induction, which is the principle behind transformers. With mutual induction, that changing current also creates a changing magnetic field that can affect another circuit that is electrically isolated, but it's magnetically connected. So if I were to have one circuit and right beside it another circuit, that changing magnetic field of my first initial circuit will induce a voltage in the secondary circuit, which is the process of transformers. Here we have a more typical mutual induction setup that we would see in a transformer. My 120 volt supplied side is creating that magnetic field. Then that magnetic field is then enhanced by the iron core. Since my secondary side, my 60 volt side, is going around the same iron core, the magnetic field is connected. This means my two different coils are electrically separated, however they're magnetically connected. An important thing to realize is that in a DC circuit, the only time we have a changing magnetic field is when we energize or de-energize the circuit. Therefore, induction only happens during that energization or the de-energization. The rest of the time, I don't have a change in magnetic field and I don't have induction. This is why transformers don't work with DC. As soon as I reach that steady capacity, I stop my induction and I will not produce any voltage on my secondary side. In an AC circuit, I have a constantly changing current, which creates a constantly changing magnetic field. Therefore, since that magnetic field inside that core is constantly changing, I have constantly produced voltage on the secondary side. The amount of voltage on the secondary side is all dependent on the ratio of turns between the primary and the secondary. If I have 10 coils on the first side, my primary side, and I have 5 coils on the secondary side, I'll produce half the voltage on the secondary side. So the ratio of turns inside a transformer is the same as the ratio of the voltage that's being produced between the primary side and the secondary side. The other type of induction that we have is self-induction, which occurs in every single type of coil that we have. The basic principle behind self-induction is the fact that the growing and collapsing magnetic field of one turn of the coil is affecting the turns that are directly around it. So as I have that growing and collapsing magnetic field on turn 1, it is cutting across turn 2 and possibly turn 3, 4, 5, and 6, all depending on the strength of the magnetic field and how many conductors are piled together. As that magnetic field crosses the next turn inside my coil, it is producing a voltage inside that turn as well. And that voltage opposes the initial creation of that magnetic field. This is where Lenz's law comes in. Lenz's law states that the polarity of any induced voltage must be such that any current resulting from it develops a flux that tends to oppose any change in the original flux. Therefore, if I consider my DC circuit, as I close it and I have current rise, and I think about my left-hand rule for current, as my magnetic field grows across the next conductor, it's going to create a current in the direction that is opposing the initial current. Now, as I open up my switch and I have a collapsing magnetic field, I've changed direction of the magnetic field. Therefore, I have also changed direction of the induced current. So now, instead of opposing the initial current, as that magnetic field collapses, it aids the initial current. So now it's going in the same direction. This is why induction is a process of opposing the changing current. The initial direction of the magnetic field is creating a counter current that is going in one direction, which is in opposition to the initial current. And as I change direction of my magnetic field, I also change direction of that induced current, which means now my induced current and my original current are both going the same direction. To be more accurate, the process of induction actually creates a counter EMF, and this is the process of which creates our counter current as well. The counter EMF that's created by induction is dependent on 2 different factors. First of all, it will depend on what the inductance of the coil is. And if you remember, inductance of the coil, it depends on the entire process of how that coil has been put together. The other thing that affects the amount of counter EMF is the rate of change, or the frequency that we have, whether it's 60 hertz or 40 hertz or 120 hertz. The faster I have that change, the more induced EMF I'm going to have, so more counter EMF I'm going to have. We have a formula which says counter EMF is equal to the change in current divided by change in time, which is my rate of change, multiplied by the inductance of the coil. So the counter EMF is both directly proportional to the rate of change as well as directly proportional to the inductance of the coil. You've reached the end of part 2. Please make sure you review this lesson and read your module, and then return to Blackboard to do the worksheet. Also complete the self-assessment, and then you can continue on to part 3.